To figure out a formula, chemists need a counting unit, which is some way to represent a pretty large amount of atoms in just a small, succinct way. And the best analogy for the mole is to talk about a dozen, because if you went to the store and you got a dozen roses, all right, you would get 12 roses. And if you got a dozen donuts, you would get 12 donuts, no problem. You could also get half a dozen donuts, which would be 6 and stuff like that, okay? So people generally know that a dozen is 12 and 12 is a dozen. Well, the mole is something similar. It's just that the mole has a number associated with it. It's just a crazy big number. Now, the mole is one thing that runs around my backyard sometimes and causes molehills, which kind of drives me crazy. It's a long story. I'm in therapy working on it. No, I'm just joking. The mole is an interesting thing, but this isn't the little critter that runs around in the back of your thing. It is, like I said, similar to a dozen. And you can have dozen roses, dozen donuts, all that jazz. Well, you could have a mole of roses and a mole of donuts, but you wouldn't dare, as we'll talk about. It's an insane number. The mole was first proposed by this guy, Ostwald, 1893, and it's been very useful, honestly, for chemists since it was first discovered and proposed. Like I said, a dozen is about 12. A mole is equal to 6.022 times 10 to the 23rd. So let's just think about that for a little bit. If I said, go get me a mole of donuts, you would need 6.022 times 10 to the 23rd donuts. And that's a big number. Here's something to kind of help you make sense of it. 10 to the 9th is a billion. So if you had a billion, that would be 10 to the 9th twice, or 10 to the 18th, a billion donuts. And 10 to the 18th is still smaller than 10 to the 23rd. So every time we talk about a mole, just realize we're talking about more than a billion. And it can be grams, it can be carbon atoms, it can be caffeine molecules, it can be anything you want, but it's just a freaking large number. Literally, if I have to use G-rated terms in my classes and stuff, so freaking came out, but you can put your own F word in. But anyway, every time we talk about a mole, it's 6.02 times 10 to the 23rd. And they call this Avogadro's number because Avogadro was the first person to propose it. The symbol for Avogadro's number is N sub A, like that. We'll see that once in a blue moon. It's hardly crazy. Now, the mole is now defined as the same number of pieces, atoms, molecules, donuts, whatever you're using, as the number of atoms in a pure sample of carbon-12. And that carbon-12 has a mass of exactly 12 grams. So check this out. Let's say you had pure carbon-12, no isotopes except for carbon-12, which is hard to do, by the way. Then pure carbon-12 would have a mass of 12 grams, and you'd have 6.022 times 10 to the 23rd atoms. So if you could look at the number of atoms in that 12 grams of carbon-12, it would be 6.022 times 10 to the 23rd. And that's pretty cool. And this is how the whole periodic table is organized, which is just amazing. So all the isotopes of carbon, which is carbon-12, carbon-13, carbon-14, stuff like that, the molar mass, which is a term we'll use, comes out to be 12.011. So pure carbon-12 would be exactly 12 grams. All the carbons together, 12.011 grams per mole. So Avogadro's number is 6.022 times 10 to the 23rd, and that's the number of pieces in a mole. So if it's in terms of atoms, it would be that many atoms in a mole. If you got that many roses for a significant other, that would be 6.022 times 10 to the 23rd roses in a mole. It's just an incredibly big number. Sometimes Avogadro's number is called the chemist's dozen because dozen is too small. We use a bigger number, but it really is kind of the same thing. The molar mass was a term I used earlier, and that's the grams that are found in the element in a mole. And this is actually a pretty easy thing to kind of figure out, which is really, really cool. And the cool thing is that based on the language I showed you the molar mass of any substance is numerically equivalent to its atomic mass in AMUs. So all those average masses we were talking about, like the antimony is never going to be 121.76 if you have exactly 1 atom? Haha! That number also represents the grams of antimony in a mole. And that's what's really cool. So here's the punchline. Those numbers on the periodic table, the atomic masses, have 2 meanings. If you have a single carbon-12 atom, mass is going to be 12 AMU. But if you have a mole of pure carbon-12, that's going to have a molar mass of 12 grams. So check this picture out on the right. There's 65.4 grams of zinc. 65.4 is the molar mass of zinc. You look on the periodic table, it's about 65.4 grams. So you'd measure out 65.4 grams of zinc, you would have a mole of zinc. And a mole of zinc, 6.022 times 10 to the 23rd. So in that little sample right there, there are 6.022 times 10 to the 23rd atoms of zinc. And all of those are equivalent. So carbon is about 12 grams for a mole, which is 6.022 times 10 to the 23rd. Tin in the lower right-hand corner, 118.7 grams. That's a mole of tin atom, 6.022 times 10 to the 23rd. So you can quickly weigh out huge numbers of atoms with this understanding, which is just fantastic. But the punchline is that on the periodic table, those numbers have 2 meanings. It can be the mass of an individual atom in AMU. It can also be the mass in grams of a mole of the compound. And honestly, usually we use the grams per mole, the molar mass, more than the individual atoms, but it's still nice to think about that too. Whoa. My mind gets blown every time I talk about it, I won't lie. So here's just some more examples. The average atomic mass and the molar mass for different elements, and then the atoms in a mole. And notice that the numbers in the second and third columns, they're the same. So carbon, in individual atom of carbon, 12.01 AMUs. But if you want to know how many grams there are in a mole of carbon, you would measure out 12.01 grams. And in that 12.01 grams, which is a mole, you would have 6.022 times 10 to the 23rd atoms of carbon, which is great. And if you go down to the bottom there, chlorine is 35.45. That's the AMUs, the average mass of one chlorine atom. And chlorine has 2 isotopes, so you'd find it, but it's the average mass. But who cares about that? Honestly, most of the time we use the molar mass. If you weigh out 35.45 grams of chlorine, you have a mole. That means you have 6.022 times 10 to the 23rd. That lower right-hand number there, or picture there, shows how the differences in the densities, because those are all 1 mole amounts. Sulfur is not as dense, so it takes up more space. Tin is much more dense, etc., etc. Kind of cool. I try to use at least 4 sig figs for molar mass all the time. And so for most of the elements, that means go to the hundredths. Some of the smaller ones, you go to the thousandths. But if you can have 4 sig figs, you're good to go. You don't need to use all the sig figs. I see so many people for oxygen, they're using 15.9998 or whatever the number is. You don't need that many most of the time, all right? 4 sig figs will get you by. Highly recommend the 4 sig fig value. So here's a question you might see. It says, what's the molar mass of an element with an atomic number of 12? Well, atomic number of 12 means the number of protons in that particular element. And atomic number of 12 would be 12 protons. On the periodic table, that's magnesium. So it wants the molar mass of magnesium. That's the other number in the entry for magnesium. And if you look on your periodic table, it should be about 24.305. Now, every periodic table is going to be a little different. Sometimes you'll see 24.31. You'd round the 0 up because you're dropping the 5. Sometimes you see just 24.305. But whatever you use, it should be about that and be pretty cool.
When magnesium metal burns, the product of the reaction has a greater mass than that of the original magnesium. John Dalton's atomic theory successfully explained this seemingly strange result.
People started to think about how the different compounds can react and do different things. And when magnesium is burned in oxygen, creates a really bright light, by the way, the little ash stuff that's left has a bigger mass than the magnesium it came from. And we now know that the magnesium is forming magnesium oxide. We'll talk about that later. But here's what's kind of fun, though. Let's say that we're going to burn 0.200 grams of magnesium. And that's a really small amount of magnesium. That would fit on your pinky, for example. example. The question is how many atoms are represented by that amount? And you can figure this out now. What we're going to do is we're going to use the molar mass of magnesium on the periodic table. Now I'm going to cut it to 4 sig figs. 0.200 is only 3 sig figs. You want to have at least that many sig figs going forward. I'm going to use one more. That seems to be a better answer. So we're going to use 24.31 grams per mole. And we can turn the grams in magnesium into moles of magnesium. And once we have that number, then a mole of anything, 6.022 times 10 to the 23rd. So we can figure out the number of atoms from there. Pretty cool. So here's what we're going to do. We'll first figure out the moles. So 0.200 grams is how much we start with. We're going to divide by 24.31 grams per mole. And you can see on there that the grams on the top cancels grams on the bottom. We're left with 8.23 times 10 to the minus 3 moles of magnesium. And that doesn't mean a lot to me. But the next part is exciting. How many atoms are in that piece of magnesium? And you must go through the mole to figure this out, because a mole of anything, 6.022 times 10 to the 23rd. So you can see now the moles cancel. We have just atoms left over, atoms of magnesium, 4.96 times 10 to the 21st atoms. So your little tiny piece of magnesium that fits on your pinky has 10 to the 21st atoms. And again, a billion would be about 10 to the 18th. So this is just massive numbers of atoms in very small quantities, at least from our macroscopic perspective. So here's a question you might see. It says we have 3.011 times 10 to the 23rd atoms of pure carbon-12. How many grams of carbon-12 do I have? All right, so this is kind of the opposite of what we did. We're going to go atoms to moles and then moles to grams. And this is a problem you might be able to do in your head, but in case, I want to show you the official way to do it, so there's no question. So the first thing we're going to do is turn atoms into moles. We're using Avogadro's. So we'll take that number and divide by Avogadro's number, 6.022 times 10 to the 23rd. That'll tell us how many moles. And we're going to see it's half of a mole. And then it says we want to know how many grams of pure carbon-12 we have. Well, carbon-12 is exactly 12 grams per mole. So when you do the math out, it comes out to be 6 grams of pure carbon-12. That's how much you would be holding if you had 3.011 times 10 to the 23rd. So very small amounts in our day-to-day world can have huge ramifications in terms of numbers of atoms. Kind of fun to figure it out. If you want to find the molar mass of a compound, you absolutely can. So let's say you want to find the molar mass of ethanol, which is C2H6O. Well, ethanol with C2H6O has 2 carbons, 6 hydrogens, and 1 oxygen. And carbon is 12.01 grams per mole, hydrogen 1.01 grams per mole, and oxygen 16.00 grams per mole. And again, all these numbers are coming from the periodic table, and I'm raising them to the hundredths because that's all we need, as it turns out. So then to figure out how much carbon it would be, there would be 2 times 12.01 or 24.02 grams of carbon. 6 times 1.01 would be 6.06, and we'll add that to 16.00 for oxygen. So the molar mass, which is the total mass then in this case, 46.08 grams per mole. And that's how you calculate the molar mass of a compound. You just multiply the individual elements by how many you have, add them all together, and you're good to go. So all of you can calculate the molar mass. It's no big deal. It is sometimes helpful if you have a molar mass calculator. And online or through free apps, you can get molar mass calculators. You put a formula in, and it will spit the molar mass out, which can be really helpful. I use one all the time. You can too. It's not that I can't do it myself, but it is sometimes nice to have a little assistance in this, which is something we do a lot. Tylenol is C8H9NO2. And so when you figure out its molar mass, add up all of those and add them to the different things, 151.16 grams per mole. And there in that picture are some other ones. Aspirin, about 180.2 grams per mole. That copper 2 chloride dihydrate thing is 170.5. Water, 18.02. We're going to use that a lot. And again, try to use at least 4 sigs for molar mass. All right. So 4 sig figs will get you by 5, all of those numbers are 4 sig figs. That's why it's good. You do not need to go more than 4 sigs most of the time. If you happen to have 5 sig figs, then maybe you'd have to find a 5 sig fig molar mass. But trust me, most of the time, 4 sig figs, you are good to go. So water, so important, all right? And I'm putting it up here as a special thing because I want you to know it. Water. Add up 2 hydrogens and 1 oxygen. Oxygen 16.00, hydrogen 1.01 times 2, 18.02 grams per mole. And we're going to use that molar mass a lot. So it's a good number to start throwing in your brain. We'll use it. We'll use CO2 a lot, which is 44.01, but we'll talk about that at a different time. Just know that water, 18.02, good to go. Here's another example of a kind of problem you can have. This one involves saccharin. Now, saccharin is an artificial sweetener, kind of like NutraSweet, and there's the formula for saccharin as well as its molar mass. And so let's say that we have 0.0400 grams of saccharin, and we were curious how many molecules of saccharin we have, as well as how many carbon atoms are in our sample. All right, so this is the kind of problem and stuff you might see. So anyway, what we're going to do here, we're going to turn our grams of saccharin into moles using the molar mass. And from the moles, we can turn it into number of molecules by multiplying by Avogadro's. And then finally, when we want the grams, number of carbons, there are 7 carbons per saccharin. So let's see, and there's the structure of saccharin in the upper right-hand corner there. Well, anyway, here's turning the grams of saccharin into molecules. And here's the grams of saccharin. This is the molar mass of saccharin. I want the grams to cancel, so I'm dividing by the molar mass, and that'll turn it into moles. And then a mole of anything, 6.022 times 10 to the 23rd, and to 3 sig figs, which is what we're doing here, 1.31 times 10 to the 20th molecules are present, molecules of saccharin are present in our 0.0400 gram sample of saccharin. But how many carbon atoms are there? And that's a great question too. Well, in every saccharin molecule, there are 7, as I said, carbon atoms. So if we take that number of molecules and you multiply it by 7 carbons per saccharin, you can see how the saccharin molecules cancel out. You're left with just carbon atoms, and lo and behold, 9.17 times 10 to the 20 carbon atoms are in your saccharin sample. So again, it's just fantastic how many atoms we consume on a normal basis. It's amazing. This will give you all the tools that you need to answer this for yourself if you ever want to figure it out.